The microstructure of calcium silicate hydrates. Hydrated cement systems can be complex in terms of hydration products. Nonetheless, CSH is the hydration product that occupies the majority of the space in a hydrated cement paste, and it's responsible for many important processes. So to understand it, we'll start off with the atomistic structure of CSH. CSH has no long-distance order, so most characterization techniques cannot reveal the exact atomistic and nanoscale structure. One of the latest models developed to describe the structure of CSH is the brick model, and in this image you can see a brick unit of CSH with a calcium to silicon ratio of 1.5. The blue spheres are calcium ions, and they are on top of silicate tetrahedra with the 4 small red spheres of oxygen, as well as water, the white and red symbols. Here's a better look at the model, this time with a 360 degrees rotation along the C-axis. An atomistic model should take into account all of the experimental evidence. Additionally, it should give some indications to why CSH displays the rather unique properties that it does. The consistently nanoparticulate nature of CSH, or variation of chemistry. Unless the models can be satisfactory when confronted with the experimental evidence available, they leave several questions regarding the properties and behavior of CSH unresolved. The objective of one of our colleagues from ERICA is to model the adsorption of ions and small organic molecules onto the surface of CSH. These ions and small organic molecules can change the morphology of CSH and consequently the properties of the hydration product. By using atomistic simulation, like molecular dynamics with LAMPS code and metadynamic simulation with Plumet code, one can adequately simulate the adsorption of these substances. Now, let's focus on the CSH solid. Imaging CSH is possible with techniques such as scanning electron microscopy, or SEM, and transmission electron microscopy, or TEM. CSH in cement has often been observed with a fibril-like morphology as it grows from alite. However, there have been many questions revolving on why this hydrate takes this form. To better understand how external parameters affect the morphology of CSH, synthetic CSH was formed in the absence of other cementitious hydrates like portlandite and ettringite. Restraints on space for growth and chemical limiting reactants are effectively removed from the system to study CSH alone. In this method, we carefully control pH, temperature, and mixing conditions as calcium nitrate tetrahydrate and sodium metasilicate are added to one another, forming CSH. This synthesis allows us to see how the presence of different substrates and other materials and cement may affect the morphology. Pure single-phase CSH shows a disordered nanofoil morphology. Synthetic CSH produced by the same method was made in the presence of D-gluconate, a small sugar that can act as a retarder in cement production. While CSH normally arranges itself in disordered nanofoils, the addition of D-gluconate caused square aggregation or possibly bipyramidal aggregation, suggesting that additives or additional substrates in synthesis may have an ordering effect on the precipitate. The objective for one ERICA project is also to study the influence that aluminates and sulfates have on the morphology of CSH formed by dropwise precipitation. Now, let's look at the microstructure of CSH. At microscopic level, CSH is the matrix that surrounds all of the unhydrated clinker grains and the other hydration products, including portlandite, ettringite, and monocarbonate. In this micrograph, we can even observe 2 types of CSH that are formed in a hydrated paste, the inner and outer product. When we talk about macroscopic properties such as transport or strength, it is the whole microstructure which is responsible. But how exactly do gases and small species migrate through the matrix of the hardened cement and concrete? The answer is the CSH pore network in the pore solution. Let's talk about the pore network. The widely used method to obtain information about the pore structure is the MIP. This can give the total porosity and the critical entry radius. Capillary porosity includes all spaces that are not occupied by hydrates of unreacted clinker grains. This category of pores is refined during hydration as more hydrates are formed and clinker particles are consumed in the reaction. This is why MIP can be used to study the refinement of porosity in some blended cements. Nanometric pores such as gel pores cannot be totally intruded by mercury, which is why the proton NMR technique is extremely useful for cement. One of the projects in ERICA deals with the understanding of how the transport of chloride would take place through a microstructure of only CSH. For this purpose, a homogeneous CSH was obtained by hydrating a reactive B-light. This is presented in the image on the slide. We see how the hydrated matrix contains no portlandite and just one type of CSH. Further addition of silica and metakaolin to this binder and their effect on the CSH composition and porosity is being studied. The reason why we are interested in the transport of chloride is because it is responsible for a very serious durability issue, the corrosion of stainless steel used as a reinforcement. Corrosion products, once formed, lead to the expansion and cracking of the matrix, which is extremely dangerous for a concrete structure. So this takes us to the mechanical properties of cement. Strength is one of the most important properties in a cement paste because it dictates how we design structures. Strength can be defined as resistance against failure, and when we talk about strength of a cement paste, we usually refer to uniaxial compressive strength. Strength can be influenced by several properties, mainly water to cement mass ratio, fineness of a cement powder, and also the temperature. Uniaxial compressive strength of a cement paste can be obtained experimentally by testing cylindrical samples by a universal testing machine. During testing, loading force and displacements are measured. These are subsequently recalculated into stresses and strains. Stress is applied force over cross-sectional area of a sample, and strain is a ratio of contracted and initial length. So, the output from the compressive strength test is a stress-strain diagram from which we can read the strength of a cement paste. This is the ultimate stress at which a cement paste has failed. Apart from experiments, strength of a cement paste can be predicted numerically without touching a grain of cement. This can be done by means of continuum micromechanics, which provides a link between microscopic material properties and macroscopic mechanical properties. So, we can do a numerical prediction if we know these key features of a microstructure, including shape of constituents, types of interactions, volume fractions, and their mechanical properties. Here, we have an example of a microstructure of a cement paste that consists of clinker inclusions embedded in hydrate foam matrix, which is, at smaller scale, resolved as direct interaction of hydrate gel needles and capillary pores. The 2D sketches in the left bottom corners show qualitative properties of 3D volumes. Strength of a cement paste is governed by strength of the hydrate gel needles. Therefore, for strength modeling, we also need to know the strength properties of microscopic hydrate gel needles. Then we can virtually load a micro-heterogeneous cement material, which results in stress fluctuations throughout its body. The stresses within hydrates are averaged, and subsequently the most stressed needle orientation is sought. This stress value is inserted into a failure criterion, which tells us whether the stresses in the most loaded hydrates reached their stress limit. If this is the case, these hydrates break, which causes the chain effect of breaking other hydrates as well. And it leads to the failure of the overall material. Then we can say that the strength of a cement paste has been reached. In summary, we have discussed the atomistic modeling of CSH, synthetic CSH and CSH made from reactive B-light, which allows us to analyze CSH apart from portlandite, and studies of mechanical strength and transport, which will help us engineer more durable materials. Thank you for listening, and we would like to thank the EU Horizon 2020 Research and Innovation Program for making this research possible. We hope you have learned much about the microstructure of CSH. Please make sure to check out our other videos created by the entire ERICA team.